Welcome to the online lecture on the T-statistic. Today we're going to be talking about independent groups designs. Independent groups are going to, designs are the kind of T-statistics and the kind of T-test we'll be using for between subjects designs. Between subjects designs, again, are independent groups. And so we can use this independent group statistic for these between subjects designs. I hope, again, that you've gone through and either reviewed your notes and your content from 3510 for single sample t-tests, or that you've gone through the brief review that I provided on D2L. Again, it's going to be important to really remember those as we move forward, especially when we get to repeated measures t-tests. I did want to do a brief review of a couple more things before we get into the new material. So first, degrees of freedom. Remember, this is the formula for degrees of freedom. You take the number in your sample and you subtract 1 from that. Degrees of freedom are the number of scores that are free to vary. That's why they're called degrees of freedom. So we've got a little example of that here. If we know that the mean of 3 scores is 4, so if we have any 3 numbers and we know that the mean of those 3 numbers is 4, the equation looks like this then. We know that score 1 plus score 2 plus score 3 divided by 3 is equal to 4. And suppose you also know that score 1 is 2 and score 2 is 4. Well, then what is score 3? Well, because we already know scores 1 and 2, score 3 must be 6. It is not free to vary because we already know scores 1 and 2. So in the given set of 3, the degrees of freedom is 2 because only 2 numbers are free to vary. The same would be true if you picked any other 2 numbers. You could put them, and then that third value can't vary. It can't be a more random number because you've kind of pigeonholed it in. So we only have 2 scores that are free to vary, hence that degrees of freedom 2. Really remember this formula. You've used it previously. You're going to continue to use it throughout the duration of this course. So it really is going to be important that you remember this. And we're going to build upon this basic formula of n-1. So again, really, kind of tattoo this on your brain because it really is important to understand this. And if you're having problems with understanding the concept of degrees of freedom, please come see me and we'll hash that out so that we really, again, have a clear understanding of this before we move forward. Another thing that I wanted to review was kind of notation issues. Remember the difference of Latin versus Greek. So Latin letters, like our regular letter M there, are what we use for samples. When we're using Latin letters, and those are the letters that we're all familiar with, the S's and the M's and those sorts of things, then we're talking about samples. We're talking about the people in our study versus Greek letters, like the Greek letter mu there, we're talking about populations. So again, that distinction is important to remember as we move forward as well. And the whole reason that we're using samples in the first place is to answer questions about the population. So remember, it's really important that while we're doing the statistics on our sample data, the whole reason we do hypothesis testing and we look at significance levels is to see if we're able to make statements about the population, if we're able to kind of say that this is applicable to then the population. Because there's no point in saying, well, I know something really great and interesting about these 12 people. That's great. You know something about those 12 people, but you want to be able to take what you know about those 12 people and apply it to the greater population as a whole. So again, the distinction between the letter M and the letter mu, M would again be the mean of the sample, where mu would be the mean of the population. So again, it's really important to remember those distinctions of Latin versus Greek letters. So let's start out our t-test talk with some fun statistic trivia. The t-test was done by William Seeley Gossett, who you see here, and he was student. That's what they called him. And he was student because he studied under Pearson. So he was a a student of Pearson, which is where he got his nickname. After he did all his kind of, studying under Pearson, he became the chief statistician at the Guinness Brewery. So those commercials, if any of you are familiar with them, they're several years old, but where you have the two talking heads in the Guinness commercial, and they're passing back drinks. The dark-haired individual there is actually student T. Students, where we would get our student T, that actually is William Seeley Gossett in those commercials. So some fun statistics trivia. If you look at those Guinness commercials, that's the guy who does the T-test. That's where it came from. So it's always nice when you can talk about beer and statistics in the same slide. So the T distribution is slightly different than our normal distribution. In this graph here, you'll see that the normal distribution is the solid blue line, where the T distribution is the dotted line. You can see as a whole, they're very, very similar, but there are some marked differences. One of which is that the T distribution has thicker tails. If you look at that there, you can see they're a little bit fatter. They go a little bit higher, so then we know we have a larger proportion in the tails than we do in our normal distribution. What that means is when our samples are smaller, there's more of a chance of error. So extreme values are more likely. So again, when we have a really small sample, we're more likely to have an error because there's more of a percentage in those fatter tails. So sometimes we need to go further off than 5% cutoff to really be more conservative. A comparison distribution is what we're going to be comparing our research against, our statistics against, is the distribution of T's. So instead of it being just a T distribution, it's a distribution of T's. It's still T-shaped. It's still going to still have that same shape with the fatter tails, but it's still unimodal. It still has the one mode, and it's still symmetric, just like the normal distribution. But again, we have those fatter tails. And the really important distinction to remember about the T distribution is that there are many, 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 many T distributions. And the T distribution depends on the sample size. It's not the same drawing, it's not the same graph for every sample size. It really depends on the number of values you have in that sample. And so what we'll do is we'll actually say what T distribution we're talking about, and we'll use degrees of freedom to tell what distribution we're talking about. So again, it's a family of distributions. It's not just one. We have one T distribution for each degrees of freedom. And so that's why we have those T tables. That's why we don't have just a set number that we can look up cutoffs, because every single degrees of freedom has a different T distribution. Again, this does approximate the shape of the normal distribution, but because it has fatter tails, it's a little bit flatter, you saw in the graph before, than the normal distribution, which also means it's more spread out. That more variability, fatter tails in the T distribution, all of these again make a big difference when we have a smaller sample size. These aren't as much of an issue when you have a really large or sufficiently large sample size, but a really small sample size that can be very, very problematic because we have a lot more proportion in the tails than we do in a normal distribution. And so what we'll use is the table of values for the T for our hypothesis test. So if you look in the back of your textbook, you're going to have a T distribution there to look at. So again, and on the exams, you'll be given the T distribution as well. So please kind of put a flag in your textbook because you're going to need to be looking at that. And we're not going to be looking again at these normal distribution tables. We're going to be looking at the T distribution table. If you're looking in the 7th edition of your statistics textbook, I believe it's on page 588. So again, flag that for yourself because you're going to be referring to it often. And I will provide a copy of that for exams. So here's an example of a T table, and you see, if you look at the T, let's look at it and kind of see how it's broken up. It's broken up into two different kinds of hypothesis tests, one of which is one-tailed tests, and we'll get into those, and the other of which is two-tailed tests, and you can see that there's graphs that approximate that as well. Then they also talk about the different cutoff levels. Obviously, 0.05 is the lowest or the highest that we're going to be dealing with. So 0.05 and 0.01 are the ones that we'll be looking at. We won't ever really look at the 0.1 column. And then what you do is you go look at your degrees of freedom, and if we're dealing with, as you see kind of highlighted on this graph here, if we're looking for the t-distribution for a one-tailed t-test with an alpha level of 0.05 and a degrees of freedom of 15, our cutoff value would be 1.753. If we're looking at 0.05 and we're looking at a cutoff, a degrees of freedom of 3, we would be looking at 2.353. So again, it kind of depends. If we're looking at degrees of freedom 8 for a two-tailed test, for a 0.01 distribution, we carry the kind of look across the line on 8 there and look down to 1, and we're dealing with 3.356. So again, get familiar with these tables, really understand them, because the last thing you want to do is on a test is kind of trying to remember how to do this, use this table. You really want to be comfortable with that from the get-go. So if that example of a two-tailed test, a t-distribution of 3, we have 2.53 in the tails. The comparison distribution, this is a nice little graph that I like to show because it kind of shows the relationship between the population, the comparison distribution, and the sample. So our population is normal. Our population is not necessarily a t-distribution because it's not a sample of t's, it's a sample of people. And so in a t-test, we're assuming that our population is normal. What we're then comparing our sample against, though, is not this normal curve, but is this t-distribution. The t-distribution is, again, very similar to the normal distribution in several ways. It will have the same mean, those sorts of things. But again, it's going to be it's going to have a different shape. And then our sample, we're comparing then our sample mean essentially to that of the comparison distribution, which again has the same mean as the population, and to see if this is something that we would normally get. Is this something that fits inside this normal range for this population, or is this a really a high score or a low score? Is this an extreme score? What are the chances of us getting this score? And here in this example, this 3.2 is way off in the tails. And so we'd be able to say that we were able to reject the null in this example because our sample mean is very high compared to this distribution that we're looking at for this population and this comparison distribution. Again, it's important to remember that we're using samples to make generalizations about the population. And statistically, kind of the go-between is whatever statistical tests we're doing. So in this example, we're dealing with t-tests, so our go-between is a t-distribution between this normal population and this sample size this sample that we have. So again, to remind ourselves, most research studies compare 2 or more sets of data. Sometimes it's more than 2. For a t-test, though, we can only use 2. So we're only looking at 2 groups here. So this is the perfect test for your experimental versus your control group. Perfect, perfect, perfect. You wouldn't want to use it. In fact, you can't use it if you had a control group and 2 experimental groups. You wouldn't be able to use this. We're again dealing with 2 groups here. And that's what the t-test is suited for. So, and what the independent measures or independent groups t-test is set up for is for 2 completely different participant groups. So this is again that between subjects or independent groups design. Again, we're dealing with independent groups. They have nothing in common. We're not even talking about matched groups here. These have to be completely separate groups where we have completely random assignment to both groups. So again, here we're talking about your experimental group and your control group are the perfect example, where they are two separate groups of individuals. So you may have 20 participants in your control group and you have a separate 20 participants in your experimental group. And then we can use the independence group or independent measures t-test to compare those two groups. If we're talking about a within subjects design or repeated measures design, then we're going to be doing a different kind of t-test. So the t-tests that we're going to be talking about today are really exclusively for these between subjects designs. So these have to be independent groups. They have to be independent data to do this sort of test. The computational procedures for a repeated measures versus an independent groups test are very, very different. In fact, the repeated measures is almost easier than the independent groups because it's very similar to a one sample t-test. So they're very, very different. Each has different strengths and each has different weaknesses, just as we saw it with the designs themselves. So just as we see benefits for between subjects over within subjects and benefits for within subjects over between subjects, we're going to see that again within these statistical measures as well. So again, we're comparing two samples just to hammer this home, and the best example of that is again that experimental and control group. And again, to do this t-test for independent means, the scores have to be independent of each other. We need to have random assignment to those two groups. We're not even talking about matched groups here. They have to be completely separate. Definitely no kind of repeated measures designs would be applicable here. These need to be independent groups. Graphically, this kind of looks like this. We have population A taught by method A, population B taught by method B. We take a sample from each of those populations, and if you notice in this graph here, in this image, at no point do any of these circles overlap with any of the other circles. There's no arrows intersecting. They are completely separate, and we need that for our statistics to be meaningful in this design. So again, we're dealing with two completely separate groups here, such as a between subjects design with that random assignment. The other thing that's important to think about in these kinds of designs is whether what kind of a hypothesis we have. What is the researcher looking at? What is the researcher trying to find out? And we can have a directional hypothesis, and in that case, we'll be doing a one-tailed test. So if you remember back to that t-table we just looked at, they had a column for one-tailed tests and a column for two-tailed tests. A one-tailed test has a directional hypothesis. What that means is the researcher has predicted a specific direction of the effect. So we think that group 1 will perform better than group 2. That's a direction. We think that group 1 scores might be higher than group 2 scores. We're talking about a direction there. You can do an arrow one way or the other. Experimental group will have lower scores than controls. Again, you see direction in that hypothesis. So again, it's really important to pay attention to the questions and to the kinds of research hypothesis that we're dealing with here, because that specifies whether we're dealing with a directional hypothesis in a one-tailed test or a two-tailed test that doesn't have a directional hypothesis. If you do have a directional hypothesis, you're going to need to locate the critical region and the appropriate tail. So if we're talking about things are going to be higher, things are going to be better, we're going to be looking in the positive tail. If we're looking at something being worse, we're looking at things being lower, we're going to look in the negative tail. But we're only looking at one tail. We're not looking at both tails. It's really, really important to report this explicitly because one-tailed tests are, in some ways, can be, there can be a little bit more problematic. In a two-tailed test, if we're saying we're going to have a 5% chance that we're accepting a 5% risk that we say that there's an effect when there's really not an effect. Well, in a two-tailed test, you're splitting that 5% up between two different tails. So it's a lot harder to get into those critical regions. In a one-tailed test, if you're saying I'm going to allow a 5% chance that I'm wrong, that I'm wrong when I say I'm right, then that's only in one tail. And it's going to be a lot easier to get in that cutoff region. And we're creating a lot higher risk there. So it really is important that we talk about this very explicitly in the research report, so that people know that this is the kind of test that's used. It is going to be a little bit more sensitive because we're only looking where we actually think the effect is going to be. But again, that's going to create a situation where we have more risk. If there's no specific prediction about direction, the researcher just says, we think these two things are going to be different. We think there's going to be a difference between our experimental group and our control group. But there's no mention of direction, so that's not better or more or less or fewer, any of these kind of direction words, but just that there is going to be a difference. Then we're talking about a two-tailed test. We're not looking at the top, we're not looking at the bottom, we're just looking for extreme scores as a whole. And so then the critical region that you're going to look at, you're going to look in the two-tailed test column, and you're going to look in the critical region for both tails. So then your cutoff score will be plus or minus whatever the value is, rather it being plus, looking only in the positive side or only in the negative side. In a two-tailed test, you're going to look in both the positive tail and the negative tail, to see where that, if your your t-score falls into that cutoff region. And we're going to also still report that this was a two-tailed test, because this is more conservative than a one-tailed test. So again, you want that known that you're using a more conservative test, because if you're able to reject the null with a more conservative test, you have less risk of these kinds of errors. So for two-tailed tests, our null hypothesis is, for these independent groups, is that there's no difference between our populations. Here it's written, and this is how your text has it written, that if you look at the difference between these, they're equal to 0. It would also be okay to write mu1 is equal to mu2. That would be the same kind of notation. So that is also acceptable for that null hypothesis. The same thing to write it out, you would say, there is no difference between the population means, that the population means are the same, would be a way to write out that alternative, that null hypothesis. The alternative hypothesis is that there is a difference. They're not equal to 0. And this is again for a two-tailed test. We're talking about there is a difference. We're not equal to 0. Again, you could write that out. Mu1 is not equal to mu2. That would be acceptable as well. If we're talking about a one-tailed test, you're going to want to use those greater than and less than signs. For your research hypothesis, you're going to say just, if we're only looking greater than, that mu1 is greater than mu2. And then your null hypothesis would be that mu1 is less than or equal to. So you still are covering the entire range of the spectrum, but you're talking about direction in those hypotheses. So again, and we'll go over that a little bit more in class, and you can see the notations on those. But again, it's important to remember that we're making our hypotheses about the population, and that's why we're using the Greek notation here, because we're making our hypotheses, both null and alternative, about the populations. And then we're looking again that null hypothesis is the idea that there's nothing there, that there's no effect. And that's what we go in and we organize our t-test based on, this idea that there's no effect. And so all of our formulas are based on this idea. So then if we in fact do find an effect, that it really, chances are, is an actual effect. So in terms of the mean, if the null hypothesis is true, the two populations have equal means. So again, that's why it's appropriate to write the null hypothesis as mu1 is equal to mu2, because if the null hypothesis is true, then they should be the same. If the null hypothesis is true, again, they're having equal means. The distributions of means have equal means. Again, that's more of that comparison distribution that we're looking at. This will also, that same difference between the population will carry down into this distribution of means. And if the null hypothesis is true, the difference between these samples in our distribution will also be zero. So again, that's why the mu1 minus mu2 is equal to 0. It's the difference between those will be equal to 0 as well. So the basic structure of the t-test, the t-statistic, is this, and this is the formula from your book. There's a formula sheet posted on D2L. That is the formula sheet that you will be given on your exam, so you have plenty of chances to be familiar with it. And I've printed those out as well, and I will give those to you on class on Wednesday, so that it has this formula on there. But let's break it down. So the whole thing we're trying to find is the t, and you see that there. The different pieces that we're looking at, the top, we're dealing with both the sample means and the population means. Now, do we know the population means? If we do an experimental study and we say, okay, I need 20 participants in my control group and I need 20 participants in my experimental group, and I have 40 different psych undergrads come in and do my study. Do I know what psych undergrads typically do in these studies? Do I have that information? The answer is that I don't. I don't know what those two scores would be. I don't know what the mean of population 1 and the mean of population 2 is. But I do know that if my null hypothesis is true, there's no difference between them. And if there's no difference between them, I can take that mu1 versus minus mu2, and I can just make that value 0. So essentially then what I have is the mean of 1 minus the mean of 2, and then I subtract 0 from that. And because 0 doesn't really actually change anything there, essentially I really am looking at the difference between the means over the estimated standard error, which is what that is down there. Again, that's this estimated standard error for the sample. You notice that we're dealing with Latin there. We're not dealing with Greek. We're not dealing, so we're talking about the sample. So this is something that we're going to estimate given our actual data. So kind of written out on the t statistic is looking at the sample statistic, subtracting the hypothesized population parameter. And again, that's going to be 0 because we're saying our null hypothesis is that there's no difference between those. So the top value you can again just kind of equate to 0 and think about that piece of the puzzle is always going to be 0 in this t statistic. But again, we're comparing it against the population, and so that's why it's still a part of that t statistic. Divided by the estimated standard error. And we'll go through on how to estimate that standard error in some detail. We'll get to have more fun with sums of squares, which I know you guys have dearly missed. The independent measures t-test is again then that t statistic. Sorry about that. Okay. So the measure of the estimated standard error is the distance, but the average distance between the two means and the population parameter. So the population parameter is again based on the difference between our populations is 0. And so we're saying how much difference is it reasonable to expect between these two sample means? What's the reasonable standard error that is, and standard error is again this estimated standard deviation essentially. So the standard error is saying this is our estimated standard deviation. We don't know our standard deviation for our population. We don't know our variance for our population. So we're going to estimate it based on our samples. Our samples is the best information we have going into this statistics for our population. So we're going to estimate what our population variance standard deviation would be if our null hypothesis is true. Again, our null hypothesis is that these things are equal, that they're the same, that there's no difference between them. The difference is 0. And the way we do that is this equation. Let's break that down. That first piece there, the S subscript mean 1 minus mean 2 is the estimated standard error. That's what that represents. And you notice that in your T statistic on the previous slide. Under the square root, we've got the estimated variance for group 1, the estimated variance for group 2, divided by the number of subjects in group 1, divided by the number of subjects in group 2, and we're going to add those together. So we're basically just looking at these things and the variance of each of these, adding them together and taking the square root of that. Now this one only really works if our sample sizes are equal, which they're not always equal. Ideally, we should have equal sample sizes, but as you can probably guess by now, research doesn't always end up having ideal circumstances. So we don't always have that. So the best way to really do this is to do pooled variance. Pooled variance shows what the standard error would be if we take out this whole issue of subject size, of sample size. So again, the previous slide, the equation on that showed that it only works if they've got the same sample size. If you have 10 participants in each group, then that's an equal balance between those two. If you don't, if you have unequal sample sizes, then that is a very biased kind. You're going to weight your variance in favor of the one that has more participants or less participants. It's going to get unequally weighted. So again, by doing pooled variance, we eliminate that. So pooled variance provides an unbiased estimate for calculating that standard error. And so a lot of the times it's just kind of best to do pooled variance because you don't have to worry about sample size. Again, you still can look at it, and you can do the other if you have equal sample size, but essentially they come out the same. So, and if you have equal sample size and you do pool your variance, you will have the same value as if you do the equation the other way. So this is the equation for pooled variance. And again, there is a sheet on D2L that has all of these equations on them. I do not require you to memorize equations. You need to know how to use the equations, and you need to know which order to use the equations in. And hopefully we will get enough practice both in the materials provided for today and in class and through your problem set that there should be no problem when we get to the exam. So this is the equation for pooled variance. If you look, we have the top, we have sums of squared 1 and sums of squared 2. So sums of squared for group 1, sums of squared for group 2, divided by the degrees of freedom added together for both of those. You see we're adding these things together. And we're not doing them separately, dividing them separately and adding them. We're adding them together and then dividing them, which is the pooling part. That's where we're pooling all our sums of squared together. We're pooling all our degrees of freedom together, and then we're dividing it so that we're having an equal measure here. Everything's equally weighted in terms of variance between the two groups, even if we have unequal sample sizes. So again, this is going to be unbiased regardless of equal sample sizes or not. And again, this can be used with equal sample sizes as well. It'll come out the same. So again, back to the same equation we had. Here, all we've done is replaced it with the pooled variance instead of the variance for each of the groups. We replaced those, instead of it being s squared 1 and s squared 2, we have the pooled variance for each of those. So again, it comes out the same. It just really depends on if you're dealing with equal groups or not. So again, what's important to remember with both of these equations for the estimated standard error is it's how much difference do we expect between these two samples if the null hypothesis is true. And remember, the null hypothesis is that there's no difference between these two samples, that there's no difference between, we won't see any difference between these two samples because there's no difference between our populations. And again, remember, that's the really important distinction, is we're taking samples to make conjecture about the population as a whole. Degrees of freedom, it's still that same basic formula, but because we're doing two groups, it looks a little bit more complicated. So what we'll do is we'll take the degrees of freedom for the first group plus the degrees of freedom for the second group. We'll add those together, and that's our total degrees of freedom. And if you notice, this is the same as the denominator for the pooled variance. So it ends up being the exact same thing, degrees of freedom 1 plus degrees of freedom 2. So if you have 10 participants in each group, and you say, okay, well, what's degrees of freedom for group 1? Let's think about that. I'll give you a second. If you have 10 participants, the degrees of freedom for 1 would be 9. If you have 10 people in your second group, the degrees of freedom for that would be 9. So you would take 9 plus 9, add them together, and you'd have 18. That would be your degrees of freedom. 18 is then the number you would use to look at your t distribution, to figure out which t distribution you're talking about. It would be T18 is your t distribution then that you're looking at. So you have to add those two together to find your cutoff values, to find that critical region, to where to look at that. There's a couple of assumptions that we have to meet to be able to use this independence mean measures t-test. We already talked about the first one, the first two, in fact. The first is that within each sample, the observations must be independent. Again, we have random assignment to these groups. It had equal opportunity to be in these two groups, and in no way is there any kind of overlap between these two groups. Remember back to the graph with the big blue circles, the smaller blue circles, and the arrows, and we saw no overlap between those. Again, the observation within each of these really need to be independent. The two populations from which we selected these samples, again, must be normal because the t distribution is based off of the normal distribution. Again, we're assuming that these have a normal distribution, and so we need that to be met. If we don't have a normal distribution for the population, the t-test is not going to be the best solution. And that the two populations from which the samples are selected should have equal variance. This is called homogeneity of variance, and we'll spend some more time with this in the next lecture. And there is a way that we can check to see if this criterion is met, and we'll do that in class on Wednesday. In the literature, we saw this in our ERS. You're going to report whether there's a difference between the two groups and whether it was significant or not. So when they looked at the inverted faces versus the upright faces, they saw that there was a difference, and they noted that. They reported the descriptive statistics. They gave us both the mean and the standard deviation for each group, and they gave us the inferential statistics, the t statistics, and the degrees of freedom. The degrees of freedom is important because, again, that's telling us what t distribution we're dealing with here. That t statistic doesn't mean anything unless you know which t distribution we're looking at it on. So that degrees of freedom is really, really important. And that p-value is going to be very, very important as well. So in these next slides, we have a learning check. What I want you to do is I want you to read the question. I want you to read the answers. Pause the video. Think through it. If you can answer it, great. If you can't, please go through the lecture outline. Please go through your textbook and try and find the answer. Figure out which one it is. And then unpause the video, and it will take you to the answer. And there's 2 slides of these, so please do this for both of them. So, which combination of factors is most likely to produce a significant value for an independent t statistic? So this is a question about signal and noise ratios. So remember, if you look at that t statistics, the mean differences are going to be at the top of that value, and the sample variances are going to be at the bottom. So really think about that t statistic and figure out which one of these is going to produce, most likely to produce the significant value. This is, again, your signal is going to be usually in your mean, and your variance is going to be your noise, to kind of give you some hints. But please pause the video and go find that answer. The answer is which is D, a large mean difference and a small variance, because then we're getting a large signal, which is our mean, in a little bit of noise, which is our sample variance. So again, that's most likely to produce a significant T. That doesn't necessarily mean that these others can't. It just is less likely, and it's going to be harder to do. You're going to need a larger sample size for any of the other ones to really to hit significance levels. So both of these are true, false. The next slide has the answers for both questions. So if both true or false, if both samples have 10 participants in them, the independent measures T-statistic will have degrees of freedom 19. Please pause, go look at the formulas, write out the statistic, write out the degrees of freedom, and answer that question. True or false, for an independent measures T-statistic, the estimated standard error, again, that's the equations that we were talking about where we were pooling variance, measures how much difference is reasonable to expect in the sample means if there is no treatment effect. Think about what that means, what no treatment effect means. Again, go back to the text and the lecture outline if you're, or even previous, rewind in the lecture and look to see if you can help find that answer, and then proceed to the next slide. So here are your answers. The first one's false. It's not 19. You don't add the 10 and the 10 together and then subtract 1 to get 19. You subtract 1 from each group and then add them together. So 10 minus 1 is 9, plus 10 minus 1 is 9, it equals 18. And the second one is that's an accurate interpretation. If there's no treatment effect, that's saying that our null hypothesis is true. And remember, if our null hypothesis is true, then which is what we're assuming our standard error is. And we've discussed that previously in the slides. I hope this gave you a really good overview of what this is. Again, you have the formulas on D2L. You can look at those. I want you to now go and look at a practice problem that's provided by Dr. Good. He has a video where he hand calculates that out for you. So please go watch that. After you've done that, there is a practice problem for you to work on that has the answers in that. So I really want you to do both of those things today, which is why this lecture was a little bit shorter, so you could do that. And then on Wednesday in class, we'll go over an example together, and then we'll do some more practice problems in class, so that we have a lot of time practicing this prior to your problem set that will be due a week from Wednesday. Hopefully we'll have no more inclement weather, and everything will be good to go from here. See you guys on Wednesday.